Water and Wastewater Treatment. Today we have Professor Gerasimos Lyberatos with us. He is from Technical University Athens. He will talk about application of microbial fuel cell for water and wastewater treatment, mainly focusing on wastewater treatment. As a panel experts, we have Dr. Shamsuddin from NIT Trichy. He is from Chemical Engineering Department, and Dr. Haribabu from NIT Calicut. He is also from Chemical Engineering Department. Before starting the program, I will go through just introduce Professor Gerasimos. Professor Gerasimos Lyberatos is currently professor in School of Chemical Engineering, National Technical University of Athens, and a collaborating faculty member of the Institute of Chemical Engineering and High Temperature Chemical Processes, that means Foundation of Research and Technology, Hellas. He obtained his BS at MIT, his MS and PhD at Caltech, USA. His research interests are in biochemical engineering and environmental technologies for liquid and solid waste management and valorization. He has over 200 publications in international referred journals and over 300 participations in international conferences, 9 chapters in books, and 2 books. He has supervised 35 PhD theses. He has organized 2 international conferences. Professor Gerasimos Lyberatos is editor of Journal of Hazardous Materials, Elsevier Publications, associate editor of Waste and Biomass Valorization, Springer, and is also a vice president of the Hellenic Water Association, the Greek governing member of IWA. And if you are checking his, he has more than 10,000 citations, Google Scholar citations with H index of 56. Professor Gerasimos, we are waiting for your presentation, please.
Thank you very much, Dr. Nernst, and thank you very much for all the organizers for inviting me to be with you today and give you this talk. You all know about traditional activated sludge processes, and when activated sludge was developed approximately 100 years ago, it was a breakthrough. The whole idea was, of course, that you started with organic matter, and you had microbes growing, sludge growing, and absorbing all the dissolved organic matter. So this way, you had cleaning of the wastewater. And then the problem is, of course, that you have to do something with the sludge. Typically what is done today is you have stabilization of the sludge through anaerobic digestion, and you can recover some of the energy this way in the form of biogas. But if you think really about it, it is a very roundabout way of going about things. In other words, you gain some energy, but you put in a lot of energy through the aerobic activated sludge process. So what I will talk about today, I will now share my screen. Okay. I will talk about wastewater treatment using microbial fuel cell technology, which is a very interesting alternative. The main idea is that you generate energy instead of consuming energy while achieving at the same time wastewater treatment. Okay, a few words about bioelectricity and microbial fuel cells. In 1911, Potter observed that bacteria may produce electricity. In the mid-60s, we have the first microbial fuel cells constructed. And then for a while, not much happened, but then there was a renewed interest in microbial fuel cell technologies towards the end of the past century, when Kim discovered that no mediators are necessary for electron transfer. And microbial fuel cells really represent the most recent technology based on bioelectricity. Okay, what is a microbial fuel cell? A microbial fuel cell, an MFC in short, is a bioreactor that converts chemical energy stored in the chemical bonds of organic compounds directly to electrical energy through catalytic reactions of microorganisms under anaerobic conditions. The working principle of an MFC is as follows. We have an anode compartment and a cathode compartment, which are separated by a cation exchange membrane. And the two electrodes of the anode and that of the cathode are connected through an external resistance. And you have, in the anode, you have bacteria growing, which they use organic compounds as a fuel and break it down to protons and electrons. The electrons move through the external resistance, generating electricity, while the protons go through the cation exchange membrane. And both protons and electrons are then used at the cathode electrode to reduce oxygen to water. So, in essence, you have a breakdown of two half reactions, half reaction taking place at the anode, which is the breaking down of the substrate to give you protons and electrons. And then at the cathode, you have conversion of reduction of oxygen to water. So when, for example, you use glucose as an organic substrate, you can see here what is the overall, the individual reaction for the anode and for the cathode. This, in theory, you can get 24 protons and 24 electrons from a mole of glucose in the anode, and then these in the cathode, you use oxygen as an electron acceptor to reducing it to water. It is also possible to do everything with a single cell chamber rather than having a separate anode and a cathode, because it was then realized that you don't really need a full compartment for the cathode. All you need is the cathode, electrode, and catalyst can be together, and you can have simply exposure to atmospheric oxygen, reducing that to water. As far as the biology of microbial fuel cells is concerned, the main bacterial species which are found to conduct extracellular electron transfer are Geobacter and Salmonella. And here you can see in this slide the different species that have been demonstrated to be electrogenic, in other words, to generate electricity, to be suitable for MFC. The bacteria, of course, use as an electron donor a particular substrate, such as glucose or acetate or whatever. And as an electron acceptor, they use oxygen or organic compounds. And the anode electron is used then in the place of the final electron acceptors. And extracellular electron transfer can be conducted in both direct or indirect ways. As far as indirect extracellular electron transfer is concerned, you can have a soluble metabolite or other species which we call a mediator, which in its oxidized form picks up the electrons generated through the catabolism of the substrate in the microbe and gets reduced, and then it is expelled from the cell and then goes to the anode surface where it is oxidized to give you back the oxidized form. So it works as a shuttle to transfer electrons from the species to the electrode. It is also possible to have transfer through membrane-attached electron carriers. Now, as far as direct extracellular electron transfer is concerned, it has been demonstrated that this can take place through the formation of nanowires, which you can see here. In other words, the species form nanowires through which they attach themselves to the electrode surface. or through direct contact of a membrane with electrically active surfaces using enzymes such as cytoprobes. Theoretically, at the anode and at the cathode, you can have a theoretical potential which is given by the Nernst equation, saying that the potential, the electromotive force, is equal to a reference value minus RT over NF logarithm of pi, where here R is the gas constant, T is the temperature, N is the number of electrons transferred in the half reaction of the anode or the cathode, F is Faraday's constant, and pi is the ratio of the products and reactants raised to the stoichiometric coefficient of the half reaction. For example, when you look at the anode, if you have acetate as your substrate, then the half reaction written in a reduction form is given this way, and then the potential is equal to the reference value, and then RT over 8F, because you have 8 electrons transferred, times the logarithm of acetate concentration divided by the bicarbonate concentration raised to the second power, and a hydrogen ion concentration raised to the 9th power. And correspondingly, for the oxygen for the reaction at the cathode, you have a corresponding situation where now the number of electron transferred N is equal to 4. Now, the theoretical then cell potential is simply the difference between the potential of the cathode and the anode, and this in theory is what is called the open circuit voltage. However, when we connect externally through a resistance, the anode and the cathode electrodes, then current will pass, and as a result, this will reduce the potential depending on the value of the external resistance. The higher the external resistance, the lower, of course, will be the current density. Also, the open circuit voltage, with not the open, but the closed circuit voltage, when you connect the anode and the cathode, will be further reduced by losses, which we designate as internal resistance. Now, we define the cell overpotential as the difference between both for the anode and the cathode. We have an anode overpotential and eta, and the cathode overpotential eta, which is the difference between the real and the equilibrium situation that you would have in terms of potential. Of course, then losses are due also to diffusion of substrate to the cathode and of oxygen to the anode. Then the closed circuit overpotential is given by this equation, is the sum of the two overpotentials, the one on the anode and the cathode, minus the ohmic. And this is simply equal to the difference between the previously defined EMF and U cell, the cell of the potential of the cell. Now, there are limitations in terms of performance of a microbial field cell, and these are three types. We have ohmic losses that arise from resistance of ion conduction due to the solution and the membrane, and the flow of electrons through the electrode to the contact point and any relevant internal connections. Then we have activation losses. Those are due to energy lost in the form of heat for initiating the oxidation or reduction reactions, and the energy lost through the transfer of an electron from the cell terminal protein or enzyme to the anode surface. Then you also have concentration or mass transfer losses. Those arise when the flux of reactants to the electrode or the flux of the products from the electrode are insufficient and therefore limit the reaction rate. One typically can generate what is called a polarization curve by varying the external resistance. You can see the difference in the current density and correspondingly in the cell voltage observed. Like I said before, the higher the resistance, the lower will be the current density. So we are towards the left of this curve. And there you typically can have, for a quite low current density, high resistance, you generally have activation losses manifested. The opposite happens when you have low resistance. There you have concentration losses, and in between you have the ohmic losses being the major situation. Now, how to reduce the losses? The ohmic losses can be limited by reducing the electrode spacing, choosing membranes or electrode coatings with low resistances, ensuring good contacts between the circuit and the electrodes, and increasing solution conductivity and buffering capacity. Activation losses can be reduced using improved catalysts at the cathode, different bacteria on the anode, or by improving electron transfer between bacteria and the anode. And finally, concentration losses can be limited by stirring. I should say that using a polarization curve, then you can also generate a curve of the power density as a function of the current density. The power density will be simply the product of the cell potential and the current density. And this goes through a maximum. Here you can see a typical maximum value for the power density given in milliwatts per square meter. And I should say that the internal resistance can be determined this way, the internal resistance of the cell, because it can be easily proved that it is equal to the external resistance at the maximum power density. So by finding the current density and correspondingly the resistance at which you have maximum power density, you can also determine the internal cell resistance. Now, the overall performance of an MFC is typically evaluated in terms of three different quantities. The treatment efficiency, as determined by percentage of COD removed, the power density, the power output is usually normalized to the projected anode surface, and the Coulombic efficiency. What is the Coulombic efficiency? It is defined as the ratio of the total charge, the total coulombs actually transferred to the anode from the substrate to the maximum possible coulombs if all the substrate removal produced current. For example, when we use glucose as a substrate, we saw previously that in theory you can have 24 electrons transferred to the anode electrode upon breaking down the glucose. Of course, this doesn't happen. You only have a much smaller fraction, and the ratio of the electrons actually transferred to the maximum is the Coulombic efficiency. Now, the factors that will affect the MFC performance, you have to do different things. You can do different things. One is to look at the MFC configuration used. The other is the electrode materials chosen, the proton exchange system, the operating conditions, for example, temperature, then type of microbes, type of substrate, concentration, pH, temperature, ionic strength, and external resistance. So all these parameters will actually influence the performance of a microbial fuel cell. There are different types of MFCs. Those are either two-chamber. I would say that two-chamber MFCs are mostly suitable really for assessment. And then you mainly have single-chamber MFCs for various applications. And those are of different configurations, as we see here: flat plate, a cubic arrangement, or a tubular arrangement. Various substrates have been studied. Those can be synthetic substrates, such as glucose, acetic acid, or lactose, or real wastewaters, for example, brewery, cheese factory, piggery, and domestic waste. The possible uses of an MFC include electricity production, wastewater treatment. It is also possible to have hydrogen production through what is called, I will show in a little while, a modification which is called the microbial electrolysis cell. You can use MFC for biosensors and also for bioremediation. It is really a very promising technology for wastewater treatment because it presents distinct advantages in comparison to the currently used technologies in wastewater treatment plants, such as the activated sludge process. In particular, no aeration is needed. Aeration alone, as you may know, accounts for approximately 1/2 of the operation costs in a typical wastewater treatment plant. And there is a limited sludge production. The sludge yields for an anaerobic process are approximately 1/5 those of an aerobic process. Thus, when you use MFCs, this means that you drastically reduce solids production, biosolids production in a wastewater treatment plant. And this is also, as I mentioned before, a significant limitation in activated sludge processes. So you substantially reduce the operating costs for solids handling. Finally, you can have electricity generation. The treatment process can itself become a method for capturing the energy which is involved, which exists in the bonds, the chemical bonds of the substrate that is broken down. You can capture energy in the form of electrical energy, or you can generate, for example, hydrogen gas and use it later as a fuel. Here are typical configurations of how one could do wastewater treatment using MFC technology. You use an MFC, and then, of course, the effluent will still have some COD that needs to be removed. But, of course, you need a much smaller process to do that. Or alternatively, you can use a solids contact process, or you can use a membrane bioreactor to treat the effluent from the MFC. The microbial electrolysis cell, now that I mentioned before, aims at production of hydrogen. Thus, for example, in the anode, you can have breaking down of acetate to give you protons, electrons, and carbon dioxide, of course, which evolves. And at the cathode, which is anaerobic in this case, you simply have the protons being reduced to give you hydrogen. I should just say that in this case, you need to provide a little bit of electrical energy to bring about this transformation. Okay, now let me give you an example of a study. The objectives of the study was to examine the effect of substrate concentration on MFC performance, to determine the maximum power density and the internal resistance through polarization experiments, and to study the MFC operation using real domestic wastewater as a substrate. The experimental setup is shown here. We used this is a simple two-chamber system, two bottles, 310 ml capacity each, connected via a glass tube. The anode electrode, we used carbon fiber paper here, and with dimensions as we see, 2.3 by 3.2 centimeters. And the cathode electrode was carbon cloth but coated with a platinum catalyst, same dimensions as the anode electrode. And the membrane separating the anode from the cathode through the glass bridge was a proton exchange membrane, Nathion 117. The operating conditions we used constant stirring both of the anode and the cathode chambers. The whole array was put in a chamber thermostated at 35.5 degrees centigrade, and the pH was maintained at 7. We had continuous aeration of the cathode chamber, and the external resistance was initially set at 100 ohms. The anode chamber was operated as a sequence batch reactor. In other words, at the end of each cycle, we emptied the liquid contents of the anode chamber and refilled it with fresh medium. The experiments involved, first of all, the startup. Then we used glucose as an electron donor, and then we used domestic wastewater as a substrate. The anode light and the cathode light are shown here. Those were an appropriately buffered solution, both on the anode light and the cathode light, to make sure that the pH was maintained constant. We used 5 successive acclimation cycles. We started with anaerobic sludge obtained from the anaerobic digester of the wastewater treatment plant with a 10% volume by volume. And we used glucose as the electron donor at a concentration of 0.4 grams COD per liter. Here you can see successive cycles. You can see the cell voltage increased. Initially, we had 1 kilo ohm was the initial resistance, external resistance, and then it was changed to 100 ohms. So those are successive cycles for the startup. The stars that you see here are the concentrations of the COD, and those may be read on the right. So the COD removal efficiency here was over 45%. Those were simply acclimation cycles. And after the last 3 cycles, we considered that the anodes the anode electrodes were sufficiently acclimated, sufficiently populated with electrogenic bacteria, in other words. As you see, this is a typical situation during a batch. In other words, the COD reduces continuously with time, but the voltage relatively fast reaches the maximum value and stays there, just like it happens with a regular battery, and it is maintained at a more or less constant level until the COD is substantially exhausted, where you see then a sudden drop of the voltage. Okay, the second part was then for the acclimated now situation. We used the glucose as substrate, and we varied the concentrations successively from 0.5 increased to 0.85 and then to 1.5 grams COD per liter. And here you can see the successive cycles. The COD removal efficiency of each operation cycle was very high for all the different initial concentrations of glucose. In other words, it was more than 90% in every case for 0.5, 0.85, and 1.5 grams per liter. And the Coulombic efficiency was the same, 16% for the relatively low initial concentrations. When we increased to 1.5 grams COD per liter, we got a Coulombic efficiency of 29%, which is considered quite satisfactory. The duration of the operation cycles increased when we increased the initial concentration of the substrate. So we ran for 100 hours for the initial concentration, then 178 for 0.85 initial concentration, and finally 409 for 1.5 grams COD per liter. So one conclusion here is that the higher the concentration of the substrate, the longer will be, of course, the duration of the cycle. Next, we did the characterization by doing polarization experiments. In particular, in all 3 cases, at a particular point when we had 0.5 or 0.8 or 1.5 grams COD per liter, we varied the resistance, the external resistance, and we generated the polarization curves that you see here. Correspondingly, you can see on the right the power density. And the almost constant slope of the polarization curves here indicates the domination of ohmic losses in the dual chamber MFC. The maximum power density was obtained when the external resistance was 2 kilo ohm and was practically constant and close to 40 milliwatts per square meter for all three initial concentrations tested. The internal resistance then was approximately 2 kilo ohms for all initial concentration. And finally, we switched to domestic wastewater. In other words, as analyte, we used two different samples of domestic wastewater. The sampling was done with 10 days difference from a wastewater treatment plant. And you can see here the characteristics of the domestic wastewater. In this case, the total COD was approximately 400 milligrams per liter. Not much difference. The main difference between the two samplings were the conductivity. And this, as we shall see, is quite important. So we ran first some cycles with the first domestic wastewater, then we switched to the second, and then we reverted back to the first, just to check whether there was a significant change in the cycle when we go back to the origin during the process. The total COD removal for the first cycle was 53% and 47% for the second. So, and then when we moved to the third and fourth cycle, it was approximately 55%. And when we went back to the fifth, to domestic wastewater 1 in the fifth cycle, it was again, it was maintained at 56%. So this is as far as the COD removal is concerned. The Coulombic efficiency ranged from 4 to 7% for the first wastewater and 26 to 33% for the second wastewater. The biggest difference between the two, as I said, was the conductivity. The average cycle operation was approximately 50 hours for the first wastewater and 120 hours for the second. And as you see here, when we went back to the first wastewater, the cycle was quite similar with the starting cycles 1 and 2 when using the first wastewater. When we did polarization experiments in all these cases, we got similar to the MFC operation with glucose. The ohmic losses dominate in the dual chamber MFC. The maximum power density obtained when domestic wastewater was treated was in the range of 13 milliwatts per square meter to 20 milliwatts per square meter, while the maximum power density for the second was approximately 40 milliwatts per square meter. And the internal resistance of the MFC was 5 kilo ohms for wastewater 1 and reduced to 2 kilo ohms for wastewater 2. We did some modeling with glucose-fed microbial fuel cells. Here you see the anode and the cathode reactions, and we use the Monod-Butler-Volmer approach to do this. We have a rate expression for the anode reaction, which you see here. Ci is the concentration of the glucose, alpha is the charge transfer coefficient, and Na is the anode overpotential. And for the cathode, we have limitation by oxygen, and beta is the symmetry factor, and Nc is the cathode overpotential. In the model, we used 3 differential equations. The first one is for the concentration of the glucose, and the other 2 differential equations are for the overpotentials of the anode and the cathode. And an algebraic equation then gives you is capable of predicting the voltage of the cell and the charge density accordingly. And here is the the fitting of the model. This is grams per liter for the anode, for the glucose. And here is the current density for the cell. The interrupted red line is the model, and the continuous line is the actual line. Here you can see some SEM electron microscopy photos of the biofilm. This is when you use plain carbon paper. This is the starting condition. Here you can see the biofilm being formed. And we see that we also have rod-shaped bacteria. And in conclusion of this study, the efficiency of the MFC when fed with synthetic wastewater was satisfactory. High CO2 removal was achieved for all concentrations tested, and the highest Coulombic efficiency was obtained for 1.5 grams CO2 per liter. These results confirm the good performance of the MFC for a wide range of wastewater strengths. The results demonstrate big variations on the values of power production and energy recovery during domestic wastewater treatment of similar strength. And the results indicate a big difference of the specific domestic wastewater characteristics on the MFC performance. The origin of the variations, provided that the ohmic component represents the major contribution to the internal resistance, is mainly attributed to the big difference observed in the conductivity of the two domestic wastewater samples. Okay, now this was a study, like I said, of a two-chamber microbial fuel cell. Then we did a significant amount of work we've done on trying to develop a low-cost single-chamber microbial fuel cell. Because, of course, if you use platinum, for example, at the cathode, and if you use lithium membranes, the cost is very large, so you cannot realistically hope that you can do wastewater treatment using such a system. So, in the effort to move towards a real wastewater treatment process, trying to reduce the cost, we developed this innovative single-chamber MFC, a single cylindrical plexiglass chamber with 4 plexical tubes placed in a concentric arrangement. Inside the chamber, you can see the tubes here. The tubes were homogeneously drilled, perforated with holes. The anode electrode basically was graphite granules. And we used, for the cation exchange assembly, we used a Gore-Tex cloth covered with graphite conductive paint and electrolytic manganese oxide. So this is a schematic. This is the experimental system, as you see, the actual photograph. And here you can see a schematic of the process. We're feeding the process through this in the bottom, and we have an effluent at the top. So another characteristic of this single-chamber MFC is that it is a continuous operation one. So we do sampling from this point. We have the 4 perforated tubes, as we see here, going through the chamber, and we have graphite granules. So wastewater is fed in the bottom, and it is then moved up and comes through the top through this effluent port. It comes out simply by overflow. We have graphite granules everywhere and graphite rods connected with graphite rods to the external resistance, and from there to the outside, to the cathode. So here you see the tubes. You see the main vessel, the graphite granules. And the reactor was operated continuously using first synthetic wastewater as a feed at a range of hydraulic retention times We started with 60 hours and then reduced it to 20, 30 hours, 16 hours, and 24 hours. And we had the continuous mode then using raw municipal wastewater at an HRT of 48 hours, and this was operated for a total of approximately 190 hours. Then we modified the municipal wastewater, as I will show, by changing its conductivity, working always at an HRT of 48 hours. The temperature and the external load in all the experiments were maintained at 30 degrees centigrade and 100 ohms, respectively. The composition of the feed is shown here. The conductivity of the synthetic wastewater was 12 millisiemens per square meter. And the main characteristics of the domestic wastewater are given here. The total COD was approximately 340 milligrams per liter. And the initial conductivity was only 1.6 millisiemens per square centimeter. We added phosphate buffer and potassium chloride in the domestic wastewater in order to increase the conductivity to approximately 10 millisiemens per centimeter. So here you can see the different periods when glucose was used as a substrate. What you see here is the COD in is the red points, and the COD out is the blue, and the cell voltage is the black one, and the cell voltage is to be read on the left, and the COD is to be read on the right. We can see that we have no significant variations in the voltage when changing the hydraulic reduction times from 60 hours to 20, 30, then 16, and then back to 24. Furthermore, when the HRT was 60 hours, the effluent COD was approximately, as you can see, removed by 84%. By increasing the flow rate, and thus reducing the HRT to 20 hours, we increased, of course, somewhat the COD of the effluent, as you can see here. It should be said then that for all HRTs which were examined, the Coulombic efficiency was relatively low, 3 to 8%. And then this is when we used domestic wastewater as a substrate. We have two periods. The first period was without adding buffer or salt, without, in other words, influencing the conductivity. And we see that when we replaced glucose with domestic wastewater, we had approximately 50% decrease of the cell voltage. The effluent COD removal was approximately 70%, while the Coulombic efficiency was again in the range of 8 to 10%, and the maximum power density was 0.05 watts per cubic meter. After adding the phosphate, we saw an increase in the voltage by approximately close to 40%. So the Coulombic efficiency improved to approximately 13 to 15%. The COD was not significantly affected. The important thing here is that we had a stable long-term operation. We had a high COD removal for all HRTs, as well as when the COD was operated with domestic wastewater. When glucose was replaced by the domestic wastewater, of course, we saw a drop in the voltage and power output occur. And the MFC performance was improved after the addition of phosphate buffer, potassium chloride, and bicarbonate, and after increasing the domestic wastewater conductivity. Finally, very, very fast, let me just show you, before I finish up, some experiments we did also with cheese whey as a substrate. This was diluted cheese whey to a final concentration of 0.73 grams CO2 per liter in a dual chamber microbial fuel cell, similar to what I showed you before. You can see here that the cell voltage increased rapidly to its final value, reaching a constant value within a few hours. And the COD removal was completed within 50 hours. And then we saw a drop, of course, of the voltage. These are polarization experiments, varying the external load from the external resistance from 0.1 to 1 kilo should be this. The current density obtained was 80 milliamperes per square meter, and the maximum power density was approximately 18 milliwatts per square meter. Using the experiment with filter sterilized cheese whey, we varied the initial concentration, and I show you here how varying the initial concentration of the cheese whey, in other words, reducing the dilution. The COD removal was not influenced, was quite high in every instance, approximately 95–96%. The duration of the cycle increased really in proportion to the initial COD concentration, when the maximum power output was not significantly influenced. And here you can see that indeed there is a very linear relationship between the initial concentration of the cheese whey and the time needed for the wastewater degradation, in other words, the duration of the cycle. And with this, I would like to conclude my talk, and thank you for your attention.
Thank you, Professor Gerasimos, for this wonderful talk. And it's already covered, in this presentation already covered the basics of MFC and some advancements in MFCs. So now it's open for a panel discussions. Dr. Haribabu, please.
Unmute your mic.
Yeah, is it audible?
Yeah,
Yes.
yeah, it's audible. Please.
Yeah, the first question is on the membranes. We have a problem in the scale-up of MFC. So the membrane is playing in a major part.
Yes.
So what is your advice on this? Is because most of the researchers, what I have seen, is working on the development of the anode, cathode, and the configuration. But the membrane point of view, most of them have used Nafion 117.
Yeah, I agree with you very much. It is a major problem, and this is why we moved away from the two-chamber MFC with the Nafion membrane. We moved to membrane-less system. The single-chamber system that I showed you is membrane-less, basically. We just use a cloth of Gore-Tex cloth, and just to make sure that we don't have leakage of the wastewater, and then we just paste that and use a catalyst, which is also quite inexpensive, manganese dioxide. So really, this, if you are hoping to do something with wastewater treatment, you cannot do this with Nafion membranes. I agree with you very much. You need to have a low-cost system. And of course, now the challenge is to speed up this system. But the system works quite well, and now we are working towards scaling this up.
Yeah, thank you. The next question.
I have one clarification in this. Hello, this is Dr. Samsudin. So your point is correct that scientists are working towards the only using Nafion membrane. But however, some research is going on polystyrene ethyl ketone membrane also. Okay, that also one of the alternative solution for the replacement of Nafion membrane. Currently, one research paper I saw that they are using the clay as a membrane, clay as a separator for anode and the cathode. That also possibilities is there. But the problem is in the using of this kind of the membrane is its internal resistance of the cell is increased. While using the Nafian membrane, internal resistance is low as compared to the other types of membrane. And also, fouling is also one of the important factor. Okay, many membranes, researchers are finding that, but the fouling problems occurs in this. Okay, so it's now many researchers is focusing on towards to avoid the fouling of that membrane. Once we achieved both aspects like reducing the internal resistance and fouling, then we can achieve the good performance alternative to the Nafian membrane. Okay, thank you.
Hello. Yeah. The next point is, what about the application of microbial fuel cell in biotoilets? Is it feasible? Because as some of the membranes, as Samsudin was also pointing out, that there is a chance of using clay as membrane. If there is a possibility of developing in a biotoilet in which MFC can be employed?
Yes, actually, it has been tried, and you can use, for example, urine. It has been demonstrated, and there is some work done by Hieropoulos, I think, in Western England University, who has worked in this venue that you mentioned, using urine actually to generate electricity. Yeah, it is possible. So different materials are studied, ceramic materials, and we are also doing work in this right now, working with different materials. The idea is always to reduce the cost and both the maintenance cost but really the challenge is great. And like I said in the beginning, it is very, very important to be able to generate electricity from breaking down the bonds of dissolved organic matter. This is very important because otherwise you do, like I said in the activated sludge process, you take up the organic matter, you make microbes with that, generate biosolids, and then you have to deal with them. But you have to give a lot of energy in an aerobic process with the aerators to do that. You can really gain energy by such a process, and while at the same time achieving wastewater treatment. Of course, we are still a way to go for having full-scale applications for big wastewater treatment plants, but it is easier to imagine how we can do it with small, relatively small and decentralized systems. But this can also be quite important because you can have some communities that are could give you some energy sufficiency by using MFCs. Yeah.
Yeah. Thank you.
Any questions? Shamsuddin, any questions? Shamsuddin left. Okay, Professor Gerasimos, I have a few questions. One is in MFC main working chamber is mainly anodic chamber, because cathodic chamber is only a supporting system in the MFC. So in that anodic reaction itself, it is consuming a lot of protons, and in your all the experiments, its pH is near to 7 or 7.8. So where is the source for protons for generation of electricity or anodic reactions? What is the source?
Sorry, can you repeat? I'm not sure I understood the question.
Okay, so in anodic chamber, the main reaction is for the generation of electricity, it requires protons.
Yes.
And in your experiments, the pH is above 7. So the source of protons for generation of electricity is not clear.
Yeah, you generate when you maintain the pH at 7, you generate protons, and the protons move through the membrane. You just have a buffer system there, which will not allow the pH to change significantly, so that the microbes are not influenced. But the protons generated the extra protons generated can always pass through the membrane, and this is the idea, that they pass through the membrane and go to the cathode electrode, where, like I said, you have a reduction of oxygen to water. Okay, the pH is an important issue, of course, but you don't want to really realistically control the pH in a process like this. This would mean very significant cost, especially for wastewater treatment. You don't want to do that. You just want to make sure that the process works sufficiently well. And as I said, it happens. I mean, you don't, in the chamber MFC, for example, we have no of the pH. But even in the dual chamber MFCs that I showed you, we did not really control the pH. We just used the buffer of hydrogen phosphate and dihydrogen phosphate, just to maintain, just keep the pH not varying too much. Okay?
Right. Okay. So in the MFC, the main reactions is taking place in the anode chamber. So is there any possibility to increase the volume of anode chamber, because our aim is to degrade the pollutants or reduction of COD and increase and get the energy from anodic reactions. So instead of going for a same volume of anode and cathode chamber, if you are increasing the volume of anode chamber, say very high compared to the cathode chamber, is it possible to improve the efficiency of MFC?
Okay, really, dual chamber MFCs with a separate anode chamber and a separate cathode chamber is not the way to go for wastewater treatment. Such a dual chamber array is good and useful for analysis and to see the potential, how much electricity you can produce, what is the influence of the conductivity, answer questions like this, preparatory questions, in other words, but not for designing really a wastewater treatment. For designing a wastewater treatment, you really need to go to single chamber microbial fuel cell. So there, basically, you have no volume for the cathode. You don't need a volume for the cathode at all. What is important is really the surface area that you have per unit volume in the anode in such a system. So that's why in my talk I first gave you, the principle and described what happens with the dual chamber microbial fuel cell, which you use to analyze the substrate and to analyze a potential wastewater. And then you really want to use this information to move to designing a proper low-cost single chamber microbial fuel cell, which is cathode-less, does not need a cathode, does not need a membrane, and can generate electricity with a relatively easy way. There, like I said, the important parameter will be the electrode surface that you have available, the surface area that you have available for electron transfer per unit volume of the anode.
Okay, thank you. Dr. Shamsuddin, do you have any questions?
Yes. Nitish, as of your point of view, you said it is anode and cathode volume should be the same. If your question is correct, means, but I will say that anode volume can be anything, cathode volume also can be anything. Okay, so we used to have anode volume which is higher than the cathode volume. So because if we use the platinum catalyst, it is that is the redox potential of the platinum, it is a very high. So that much oxidation won't happen in the anode side. Okay, we have done one work which is related to the 4 chamber with 4 anode chamber, 1 cathode chamber. When increase the anode chamber from 1 chamber to the 2 chamber, we observe the same performance. When increase the 2 chamber to the 4 chamber, the performance is reduced. So it means that we can increase the volume of the reactor, anode reactor from 1 to 3. It is giving the, up to that, it can able to give the better performance. When you go for the higher volume, like 1/3 or 1/4 of the volume, if you go there, the performance is reduced. So that much able to generate the, that much energy can be generated by this kind of systems. Okay, so no need to be a same anode and cathode one.
Okay, okay, thank you.
I have one question with Professor Gerasimos. Is there any possibility to integrate the MFC with any other system?
Oh yes, absolutely. I should say we've done a lot of work, for example, with anaerobic digestion and of different wastewaters, like organic high strength wastewaters and so on. You can use the digestate that you get from the anaerobic digester as a feed with for a microbial fuel cell and generate further electricity through MFC technology this way. This is one example. Another thing we have tried is we've been working with organic fraction of municipal solid waste, and there we've been looking at drying and shredding the organic wastewater to generate some material that can be easily handled, and in the process you generate a concentrate of a water concentrate, which is an excellent material for starting material for a microbial fuel cell. So we've done experiments and have seen that it is indeed possible to combine quite well this with. Generally, I would say that when you have low solids wastewater, or you can have a leachate with high organic strength, then this is very good material for an MFC. You can treat it reducing the COD and generating electricity at the same time.
Okay, good. And also one more question. Like, is there any possibility to use algal biomass in cathode side?
To use algal
Biomass in cathode side.
In the cathode, you mean in the cathode?
Yes. Yes.
Yes, I think I have seen this somewhere. Some people have worked with this. Yes, generally that is in a typical MFC you use anode as I said as a bioreactor. But generally, one can. The whole idea is that you always have in the anode you have a reduction. I mean, you have a substrate of some type, and in the cathode you have the electron acceptor. You can, in other words, you separate the overall oxidation into two steps in an MFC. But there have been examples where you can use a biocathode, for example. You can have in the cathode you can have a biological process as well. A very good prospect is to use carbon dioxide and reduce it to methane in biocathode, and this can be used to enhance, for example, the methane content of biogas. So you can actually use it also for CO2 sequestration. To make, but you can also use algal biomass, like you mentioned. There are many possibilities, but the main emphasis of I decided to describe today was standard wastewater treatment process and trying to to working in the direction of finding an alternative to reactivate the sludge process that will really generate energy for you rather than want energy from you.
Okay, thank you.
Okay. Thank you, Professor Gerasimos, for the enlightening lecture on MFC. As I said earlier, it is already, the basics is already covered in the first a few slides. Then you give the advancements in all these MFCs, even in the kinetic modeling of all the reactions with the Nernst equations. I also thank our panelists, Dr. Shamsuddin and Haribabu, to join with us and have a good discussion with us, with Professor Gerasimos. I thank you all the viewers for watching this program. So tomorrow we have Dr. Hugo Oliveira Vargas will join tomorrow. Its topic is on bioelectrofendon and emerging technology for wastewater treatment. Tomorrow 5 o'clock he will join with us. So thank you for watching the program. Thank you everyone.
Thank you. Thank you, Professor Gerasimos. Thank you.
Please stay safe. Best regards.